matrices and matrix operations, just very basic operations in this section. Um, when we have a new math, just like when you have something new of any kind, you always set parameters, make definitions in terms of how you can operate within that particular space or field or category. And so that's what we do here for linear algebra. We talk about systems, but we correlate the system to a matrix, and then we confine all of our talking, our discussion, to the matrix. So it's needful to talk about the properties of matrices, very basic properties here that we began with in terms of comparing matrices, talk about equal matrices, adding, subtracting matrices, multiplying a matrix by a scalar, and then multiplying matrices themselves. And then further in this section, we'll talk about definitions for the so-called transpose of a matrix. How can we transpose a matrix? The trace of a matrix. Certain applications out there require the so-called trace. And I think I somewhat leave it there. I wanted to go into section 1.4, but we'll probably just go online and look at some of the homework just to make sure that you're able to input that information in correctly. So here, equal matrices, we first define the matrix. A matrix is said to be a rectangular array of numbers, simply that. Any way you collect numbers and you can place them, we say here a rectangular array, but one number is classified as a matrix. And so you can have that. So the set of real numbers themselves individually would quantify matrices. We denote a matrix by its entry. The entry is typically the coefficient, the A sub ij, where the I represents the row position and the J represents the column position. So we can pinpoint where we are on the matrix by the entry in its subscript. Right? So that matrices are equal, or I guess before we get there, the so-called size of a matrix. The size of a matrix is denoted capital A. We always denote a matrix by a capital letter, and then followed by its size, M by N, where M is the number of rows and N is the number of columns. And we read this as, it's not M times N, it's read M by N. And so standard form for a matrix is in this coefficient matrix. Here, notice that you have indeed M rows and then across N columns. Two matrices are said to be equal. First, they have to have the same size, and then the corresponding entries in the matrix are the same. And sometimes, you know, the entries could be written a little bit different, but they still could be equal. So this first example, A and B are equal because they have the same size. What would you call this size for matrix A? A 2 by 2, right? 2 rows, 2 columns, and the same size for B. So, and we know that cosine of 0 is 1, so these two matrices are equal. You can have matrices and they can have the same entries but different sizes, and so thus they're not equal. Right? As the example there, that matrix has the same size here. You got the same entries, but they're not corresponding. So these two matrices are not equal. So notice this next example, matrix A is a 2 by 3, and then matrix B is a 3 by 2. Different sizes, so they're not equal. So a matrix, to have equal matrices, they have to be the same size, and then secondly, the corresponding entries must be the same. We can talk about adding, subtracting matrices. Very simple, but here the key is, if you're going to add, subtract matrices, they have to be, one, the same size, and then you just add or subtract the corresponding entries. So no problem there. So the key is that you can only add, subtract matrices of the same size. So the first example, we add the corresponding entries. We get another matrix of that same size. The second example, the matrices have different sizes, so obviously you cannot add them. Right? Now the crutch today is the process of multiplying matrices. That's somewhat of the strong arm that we'll talk about today, and it itself is not that strong, so not too much brain power here. But most important, two matrices, to multiply two matrices A and B, we first consider the dot or the inner product. And so maybe in high school you talked about the dot product. It is formally called the inner product, and there's a course beyond this course where we talk about the spaces that exist out in the universe, mathematical spaces. And one of those spaces, most important, is called the inner product space. And a space is said to have two strengths to it. That is, one, that there's a way that you measure the vectors in between each other. And then secondly, within that space, how is that space defined? What type of product or multiplication factor do you use? And one of the fundamental ones is called the inner product space. You've been using it all along, just hadn't classified what that space is. Calculus 1, 2, and 3 is said to be an inner product space. If you have two vectors, 2 points, that you want to measure the distance between 2 points, you use what's called the distance formula. Do you remember that? Right? The distance formula is based on a square root, right? The distance between point P and point Q. So you get this, the distance is equal to the square root, whatever. That's the inner product. That's the inner product. So and later on in this course, we'll talk about that. But you have these inner product spaces. You have metric spaces, Hilbert spaces. So many spaces out there to give your soul great satisfaction. Yeah, right. Okay. Anyway, I digress. The inner product, or the dot product between two vectors. Let's say a vector U is in the 3-tuple space, the third space. That is, it has 3 entries inside of it. And a vector V has 3 entries, V1, V2, V3, U1, U2, and U3. So we take the dot product, or the inner product, and so that's simply, you're going to add the multiplication of the corresponding terms, right? So U sub 1 times V sub 1 plus U sub 2 times V sub 2, and so on. If the space is larger than the third space, then it's definitely classified as an inner product. Typically, if it's space 2, that is the two-dimensional space, or space 3, the third Euclidean space, you can use just the simple notation of dot product, but they're all said to be inner products. If it's beyond the third space, then we definitely don't call it dot product anymore. So an example, find the dot product of these two vectors. So it's just going to be the dot product of U and V is 2 times 3. It gives us 6, negative 3 times 1, negative 3, and then 4 times negative 2 is negative 8. So we get negative 5. That's the dot product. The dot product is going to be used in multiplying matrices. right? It's going to be one aspect of multiplying matrices. Let's see. When multiplying matrices, just a couple of things is important. The order must be correct. The order must be correct. If you want the house to be blessed, there has to be a man there. That's the order. Right? There has to be a man there. And then the wife is under the husband. And the children are under the parents. That's the order. It can't be the wife as the head. It can't be the children as the head. And so everything that we do in terms of human dynamics is based on the order of mathematics. So if you're going to multiply matrices, the order must be right. You can only multiply matrices of the following format. So here I'm giving an example of two matrices, matrix A and a matrix B. The matrix A has size m by p. That is that the number of rows is m for A, the number of columns is p. For the matrix B, the number of rows has to match up to the number of columns from A. That number p has to be the same, right? So the number of columns for A has to be the same as the number of rows for B. If I don't have that, I cannot multiply the matrices. So that number must be the same. The result then, this I just call this resulting matrix C. The result is always here the number of rows of M by the number of columns of B. So the M by N. So number there has to be the same. And then the resulting matrix, what was that? Resulting size there is an M by N. Now each entry, each IJ entry in the product, each IJ entry in the result here, so each IJ entry of the resulting product is the dot product of the ith row of the first matrix times the jth column of the second matrix, dot product. So so if you think about it, for multiplying matrices, you have the first matrix, you have the second matrix. It's always, for the first matrix, you always, for multiplication, you deal with the rows, just the rows. There's rows for the first matrix times the columns of the second matrix, dot product. So it's a row for matrix A times the column for matrix B, dot product for each entry. So if I'm in the resulting matrix, so here we have, let's say matrix A, and then we have matrix B. Okay. And let's say that this is row 1, row 2, row 3, column 1, column 2, column 3. And then the result for the product, let's say this entry here is I know what it is A11. So this is row 1, column 1. So erase that and just put it there. So this guy here is going to be row 1, column 1. The next guy would be row 1, column 2. The next one is row 1, column 3. This guy is row 2, column 1. Row 2, column 2, row 2, column 3. Row 3, column 1, row 3, column 2, row 3, column 3. And obviously this is a 3 by 3. It's the 3 by 3. So those numbers are the same. So the result is also a 3 by 3. It doesn't have to be a 3 by 3. It can be different sizes, and I have some examples of all of that. But my point is this. For the resultant matrix, R1 is row 1 from the first matrix. And column 1 is column 1 from the second matrix. It's dot product. Right? Then I move over across to row 1, column 2 is row 1, column 2, dot product. Move over to row 1, column 3 is row 1, column 3, and so on and so on. Right? Let's see. So here, for example, find the product, but let's check the sizes. Always check the sizes. If the sizes don't match up to how the process for multiplying matrices, then there's no product. So here we have 3 rows, 2 columns. This is a 3 by 2. This is a 2 by 2. The key is that these numbers are the same. The result would be at 3 by 2. So the result will look like this first matrix. Right? All right, so let's see if you can do it in your head. So it's going to be here, row 1, column 1. So this is 3 times 4 is 12. And then here, plus 0 times 0 is 12. Row 1, if I go here to row 1, column 2, row 1, column 2. So it's negative 3 plus 0, we get negative 3. What about row 2, column 1, row 2? First matrix, always the rows in multiplication. Second matrix, always deal with the columns. So here this is row 2, column 1. So this is negative 4 plus 0. Then row 2, column 2. 1 plus 4 is 5. And then now down here, for this position, this is row 3, column 1. Row 3, column 1. So this is 1 times 4 is 4, plus 0 is 4. And then row 3, column 2. Negative 1 plus 2 is just 1. Now, just make sure you got it. Again, this is row 1, row 2, row 3, column 1, column 2. So this is row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2, then row 3, column 1, row 3, column 2. And we know that the result is going to be a 3 by 2. Okay. Well, let's check the size. This is a 2 by 2. This is a 3 by 2. Right? So NA. The sizes do not match up. All right? I want you to do this problem first. I'll let you do it, and then we'll come back and talk about it. Let's see if you can get that result over there. And don't trust the result by all means, because that could be wrong. So you do it. Now let's see. So hopefully when you check, that number is not right. Should be a 9. So it's the first row times the first column. So it's 6 minus 5. So that's 1 plus 8. We get 9. Then it's going across. It's the first row, second column. If you got all ones, that simply means you're just adding everything in that first row. So it's um, 1 plus 5 plus 2 is 8. And then it's the first row, third column, so that's 3 plus 10, that's 13, plus 6, right, 19. Then we move down, it's the second row, first column, so it's negative 6, 0, plus 4, negative 2. Second row times the second column, is negative 1 plus 1, 0. Second row, third column, negative 3, 0, and 3, you get 0. Third row, first column, you get 18, minus 2 is 16, plus 16, 32. Then third row, second column, they're all ones, you're just adding everything in this row here. So we get 5 plus 4 is 9. Then the last row times the last column, so it's 3 9 plus 4 plus 12, 25. And so again, it's just the dot product. Think the first row is always, the first matrix is always its rows that you're dealing with for matrix multiplication. The second matrix, you only deal with its columns, right? And just dot product, row times column. That's all. Now, let's check this guy, because well, this is a 2 by 2 and 2 by 2, so that's fine. So that should work out, right? So it's 1 times 2 is 2, and then minus 2, 0. For this position, first row, second column, so negative 1 plus 16, 15. Second row, first column, second row, first column, 8 minus 2, 6. Second row, second column, negative 4 plus 16, 12. All right. That's number 4. Look at number 5. You see the connection with numbers 4 and 5? I just flipped them, right? Here, you think about this as being A times B. Then over here, I took the same matrices, but now I'm looking at B times A. And the question that I'm dealing with for the property is, do matrices commute? Numbers commute, right? 2 times 3 is 6, right? 3 times 2 is 6. Numbers commute, but do matrices commute? Not necessarily. Not all the time. We do not have a set property that says that all matrices commute. They do not. There are a certain set of matrices that will commute, and we'll talk about that a little bit later. That's something that we want to get to. And if you ever dealt with matrices, if you have the inverse of a matrix, you know those guys commute. A times A inverse gives you the identity matrix. But other than that, no. So look at number 4. The result you got was 0, 15, 6, and 12 for A times B. Then over here for number 5, we looked at B times A, and you get negative 2, 2, 31, 14. So different. Here's something that's interesting. This is a 1 by 3. This is a 3 by 1. So the result is going to be it's a 1 by 1. Right? It's a matrix with just one entry in it. So basically, it's just straight multiplication of each term. So it's 1 times 3 is 3. Then 2 times 1 is negative 2. So it's 3 minus 2. We get 1. And then 3 times 5 is 15. So we have 15 plus 1. All you have is just 16. Or what I like to do is to take a guy like this, which is a 3 by 1, and this guy is a 1 by 3, and so we get a matrix of 3 by 3. And so all you're doing with this guy is just multiplying for that first matrix, that first number times that. It's really the column, but it's 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9. So it's just this number times that first, this matrix here, you get the first row. -1 times this matrix, you get the second row. 5 times this matrix, you get the third row. So this is just 3, 6, 9, -1, -2, -3, 5, 10, 15, and 20, 25, 30, 35, 40. Anyway. Conclusion. I just said it a moment ago, but just want to make it formal. Matrices normally do not commute, right? It's a rare case when that happens, and we discuss that possibility a little bit later on. Let's talk about transpose and the trace of a matrix. The transpose of a matrix, I want to flip it, right? If the matrix A has entries m by n, well here, Aij is the entry denoted, then the transpose should be a period there. That statement does not continue. Period. Then A transpose takes the matrix A and it just transposes or interchanges the rows with the column. Right? So if matrix A is an m by n, then A transpose is an n by m. Now, why is that useful? Well, there are probably numerous applications out there. Now, I cannot remember all of the applications that I've dealt with transposers in my life. There have been so many, and there were so many that I forgot most of them, right? But I would tell you this, that eventually you will be able to use your graphing calculator to solve a lot of these big matrices, and there'll be a question in terms of find the row space, find a basis for the row space for a system, find the basis for a column space for the system. Now your graphing calculator, it's been programmed to only crunch the matrix and reduce the matrix by row reduction, not column reduction. So if we ask for the column space, you're not on your calculator, you cannot reduce the matrix on your calculator to get the column space. So you take the matrix, you transpose it, and then you put the transpose in the graphing calculator. It reduces that using column space. Then you go back and transpose that, you get the column space. Okay? Because the graphing calculator is programmed automatically to deal with row reduction, row echelon form, row reduced echelon form. So that's the transpose. Here, examples. Find the transpose of the following matrices. So A transpose, we just interchange the rows and columns. This is 1, 5, 2, -1, 0, 1, 3, 2, 4. The rows become columns, the columns become rows. This matrix here is a 1 by 3, so B transpose would then be a 3 by 1, 3, 6, 9. And then finally, the trace of a matrix. To talk about the trace, you know, recall for the transpose, there was no question on the size of the matrix. We didn't say that it had to be square and it had to be a certain size for the transpose. For the trace, we can only take the trace of a square matrix. Now, what does that mean, a square matrix again? It means that he's square. same amount of rows as columns, right? That's right. The number of rows equal the number of columns. When you were in school, was that a phrase that people they would call other kids that he's square or something like that? I never knew what that meant. I was always thinking a square, but 9 squared is 81. So is this person an 81? Anyway, it's a hard crowd today, I see. Hard crowd. I gotta pay y'all guys to laugh, Woo! So anyway, the trace of a matrix, the sum of the entries along the main diagonal. So the main diagonal would be where the number for the row equals the number for the column. So A11, A22, A33. If it's here square matrix n by n, you do that n times, right? Just add up those entries along the main diagonal. I could show you some things in theoretical in abstract algebra where this is most useful. But here we just lay the foundation. So that's the trace, and we denote that as TR parentheses A, or just TR, the trace of, and just put the matrix there, and just add the entries along the main diagonal. Nothing more, nothing less. Again, a square matrix is any matrix with the same number of rows as columns. Also, we only take the trace of a coefficient matrix, and the trace is only applied to squared matrices. All right, well, just very straightforward to find the trace. We're adding the entries along the main diagonal, so 6 plus 1 plus 3, we get 10. What's the trace for number 11? Huh? No. It doesn't exist. It's not a squared matrix, right? You can only take the trace of a squared matrix. See how we get you on that? Boy, we get you, man. I tell you. Don't you hate that, too? I used to hate it when I was in school, because I was always the guy, yeah, 6. No! I'm sorry, And then for me, it was like, I'm not saying anything else for the rest of the semester, right? I was always that dude. I always put my mouth in my foot. But anyway, so, that's it. There's a question from the homework, and then also a question online. It says, find matrices A, X, and B that express the given linear system as a single matrix equation, AX equal to B, and write out this matrix equation. Why don't you go ahead and do that for me right now? Do you see what they're asking for? Write out the coefficient matrix A by itself, write out the matrix X by itself, and then equal to write out the column matrix B by itself. Do you see what they're saying? Okay, just do that. Shouldn't take no more than about 10 seconds. So we say AX equal to B. The matrix A would be 1, 2, 0, 1, negative 2, 1, negative 3, 0, 3, 0, 4, 1. And then the matrix X is X of 1, X of 2, X of 3. And that's equal to B, which is negative 3, 0, 1, and 5. Let's see if that makes sense. This is a 4 by 3. This is a 3 by 1, so the result is a 4 by 1. That makes sense. That makes sense. You see that? So you can clearly see this is the matrix A, the matrix X, then the matrix, the coefficient, or the augmented matrix B. Yes, sir. It's the linear combination of the entries from the coefficient, right? You see that? This is what, look at the first row. This is 1 times x sub 1, which is x sub 1. Negative 2 times x sub 2 is minus 2 x sub 2, right? Then plus 3 times x sub 3. That's equal to negative 3, right? The second row, the same thing. 2 x sub 1 plus x sub 2 is equal to 0. That's the second row. Third row is negative 3 x sub 2 plus 4 x sub 3 is equal to 1, and so on. Now do the reverse now for number 13. Express the matrix equation as a system of linear equations. Just do the reverse and you get back to something that looks like number 12 in its original form. So you write that out. You get x plus y plus z is equal to 2. 2x plus 3y is equal to 2. 5x minus 3y minus 6z is equal to negative 9.